Good evening, everyone. How are you doing today? My name still remains the same, Professor Lai Kajani. I'm excited to welcome you on the platform for today's class in CHM204. Today, we are going to be looking at the topic 7 for the week 7, where we are going to be looking in detail at other higher main group elements. Remember, we started that unit 2 last week, where we looked at the group 13 and 14. Like today, we are going to be looking at group 14. We have looked at 13 and 14. We are going to be looking at 15 and 16. The peculiar nature that makes the nitrogen family to be called nicogenes, and the behavioral pattern that makes the oxygen family, which is group 16, to be specifically named as chalcogenes. These and many more are what we are expecting today. Stay tuned and stay blessed. Today we are continuing in Unit 2 of Module 3, talking about the second and higher main group elements, which are the P block elements. Today we are going to be looking at group 15 and group 16. At the end of this topic, which is the topic 7 for week 7, the learner should be able to, number 1, know and classify the elements included in group 15 and 16. Understand the electronic configuration of this group 15 and 16 elements. Know some specific reaction involved in group 15 and group 16, or the reaction these two groups are involved in. And should be able to know the application of some of the elements in this group 15 and 16. Group 15 elements. When we're talking about group 15 elements, they are the P block elements because their valence electronic configuration ended in p orbitals. They have peculiar of 5 electrons in the outermost shell, and 5 main elements of that groups are nitrogen, phosphorus, arsenic, antimony, and bismuth. While the last one that recently discovered is moscovium, MC. The name is so given based on the scientists that discovered it from Russia, specifically the Moscow city. So to honor this town, they call that moscovium. The lightest member of this group 15 elements is the first member, which is in the second period of that group 15. And his name is no other but nitrogen. Nitrogen constitutes about 78% of the volume of air that we have in nature. These group 15 are called nitrogen family. But because of their peculiar nature and important behavioral patterns, they are given the name nicogenes. You can see starting with P and N. You remember from the nicogen, remember your nitrogen, and P that started, you remember the phosphorus. Nitrogen is the nitrogen element that was discovered last among the group. And it was discovered by the work of Daniel Rutherford and Joseph Black in 1772, together with Antoine Lavoisier. About 90% of the nitrogen is actually used to provide an inert atmosphere for processes or reactions that are oxygen sensitive. What do we mean by this? Even though nitrogen has 78% abundance in the air, nitrogen is not reactive. So it provides a non-reactive atmosphere by doing what? By sending oxygen away, which is much more sensitive in reaction process. So when you want to make sure a reaction process is not oxidized against your wish, then you have to flush in the nitrogen to provide the inert atmosphere, or you can flush in the noble gas like argon to do the same. But because nitrogen is relatively abundant in the atmosphere, it's cheaper to use to provide inert atmosphere in reaction and processes than using the argon. Such processes are the productions that are highly vital in human existence and in our day-to-day usability of material as man. Examples of such industrial processes include the production of steel, the petroleum refinery, and the packaging of the food and pharmaceuticals. The first element in this group, we said, is nitrogen. So it's important to look at how do we prepare nitrogen. The major source of nitrogen gas is actually at the atmosphere. As you can see, is made up of about 78% of the air in the atmosphere. However, the distillation of liquefied air produces nitrogen gas that have a purity level greater than 99.99. So it's very good for everyone that wants to use nitrogen from time to time to have nitrogen generating plant to be installed, because it will give you almost 100% of nitrogen gas that have 100% of purity. I mean the nitrogen gas that have 100% of purity. And that's why it's easier to produce. By liquefying the air, you are able to get 99.99% purity of nitrogen gas. However, the laboratory production of pure nitrogen gas can be obtained from the thermal decomposition of sodium azide. Sodium azide. Sodium azide has been in use for ages, and it has always added value to man. If you remember, in the recent time, the Nobel laureate that was just awarded in chemistry did work on click chemistry and apply it in biological system and in orthogonal system, and they work effectively by reacting the azide with alkyne. Here now, sodium azide can be used to produce nitrogen. So when you react the sodium azide under thermal decomposition, it breaks into sodium metal as the element, and there is gaseous nitrogen getting out that you can collect by delivery system. What are the general properties of nitrogen? The earth crust is relatively poor in nitrogen. The only important nitrogen ores, and when we are saying the earth crust, don't confuse the earth crust with the atmosphere over the air. The earth crust is talking about the soil within the earth. Can you dig it out to have a ore of nitrogen? Like the same way you have the ore of aluminum, the ore of iron from the soil that you can now refine to get the pure of those elements, like the bauxite, like the hematite. But that of nitrogen is what we are talking. It's abundant in the air, in the atmosphere, but in the earth crust is relatively poor in there. The only important nitrogen ore are large deposits of potassium nitrate and sodium nitrate in the desert of Chile and Russia. These two countries, among all the countries of the world, has a notable amount of potassium nitrate and sodium nitrate. Of course, you know potassium nitrate is made up of potassium, nitrogen, and oxygen. Now, sodium nitrate is made up of sodium, nitrogen, and oxygen. So some processes can help you to refine, to purify, to extract the nitrogen out of those ore, but it's not generally available in abundance in any other part of the earth. They are believed to have been formed when ancient alkaline lake evaporated. Hence, most nitrogen compounds produced on an industrial scale usually and almost all the time uses atmospheric nitrogen as their starting material. It's easier to produce. By liquefying the air, you can get 99.9% pure nitrogen, out of which is having 78% abundance in the air. So it's the best way to get nitrogen should have been to get it from the atmosphere. Phosphorus, of course, which is the next member of that group 15, constitute only about 0.1% of the earth crust and is much more abundant in ore than nitrogen. You see, the ore of phosphorus are more, even though the phosphorus is appearing at 0.1%. But we are saying you can really dig the soil and have soil that have phosphorus combined in an ore form that you can extract phosphorus from. You can get that more phosphorus better from that soil, much more than the way you can get nitrogen from that soil. And this may also be part of the reason why we have been explaining that the second period of all these main group elements have small size, small atomic radius, and has a lot of peculiar behavior that is different from other members of that same group that is underneath them. Like aluminum and silicon, phosphorus is always found in the combination with oxygen. You don't find phosphorus in the earth crust or in ore form with any other thing but with oxygen, like phosphate group. And there is need a lot of high energies required in order to actually isolate phosphorus from the phosphate. Reaction of nitrogen. Like carbon, which is in group 14, nitrogen has 4 valence orbitals. So it has 4 electron pairs around the nitrogen center. Nitrogen can't form long chain because of repulsive interaction between the lone pair of electrons on the adjacent atom. If you remember when we talk about carbon, carbon has 4 electron system, which is why we call it sp3. So the s orbital of the valence of carbon blends with all the 3 p orbitals to form single bond, or you can bond with only 2 of them to form double bond, or you can bond with only 1 of them to form single bond. And carbon can form thousands and thousands of carbon-carbon bonds. But when you look at nitrogen, nitrogen has its valence electron as 2s2. If you remember, nitrogen has its own valence electron as 2s2 and 2p3. You remember nitrogen is made up of 7 atomic number, so it's 1s2, which is the inner core, 2 electrons. Then the second shell, we have 2 electrons in the s orbital and 3 electrons in the p orbital. And that makes the total electron of 7. So the valence of this is this for nitrogen. And when we do that, the 2 electron of 2s2 enter singly before pairing. Then the 2p, we have just 1 electron for px, 1 electron for py, and 1 electron for pz. So in the hybridization of nitrogen, with whatsoever he wants to do, is already having a pair here that is it cannot promote anywhere, because the p orbital are half-filled. They are more stable, so they will not want to get any s orbital to jump into them and disturb their stability. So if you are to hybridize nitrogen, you will need to hybridize it with 3 things that can donate 1 electron each. Like for example, if you have this now, if 3 hydrogen has to come in, it will come and pair with this without promoting this s electron, because there is no space, there is no d orbital, there is no energetic d orbital that I can promote it to. And so the hydrogen, the 3 of them, we have to come and pair down on the p orbital. That's why we are saying, oh, nitrogen is also using s and p3 just like carbon. But in the sp3 of carbon, all of the 4 lobes are overlapped to form bond, CH4. But when you look at that of nitrogen, even though it has hybridization of sp3 like carbon, but only 3 of them took part in bonding with hydrogen, there is a lone pair of electron in the 2s orbital that was not touched. So based on this, that nitrogen center is electron rich on its head. So to be able to combine with another nitrogen to form longer nitrogen bond like carbon, it will not be possible, because the lone pair of electron on the first nitrogen is making it to be highly electron rich, and the electron is negatively charged. When another nitrogen is overlapping on it, it will also have its own lone pair which is negatively charged. Negative and negative will repel each other, so they will not like to stay together. That's why we know, even though it's sp3 hybridized like carbon, he cannot produce extensive long chain because of repulsive interaction between the lone pair on the adjacent nitrogen. The stable compound with nitrogen-nitrogen bond are limited to chains of no more than 3 nitrogen atoms, such as the one you have in this side. This side has 3 nitrogen with a negative charge. However, when you look at nitrogen, it exists in a diatomic nature. So the most stable among them is N triple bond N. Because if you look at N itself, it has a lone pair here and it has 3 packed to loop to form bond in the sp3. So if other nitrogen is coming, it can overlap on those nitrogen, on those lobe of the first nitrogen to form 1 sigma bond and 2 pi bond. So the most stable form of N2 as a gas is N triple bond N, which is highly thermodynamically favored. But when you are saying N double bond N, just like you have oxygen double bond oxygen, N double bond N cannot be thermodynamically stable. Or there's a lot of things that it needs to use to overlap. You remember there are 3 p orbitals there. And then with this 1 pi 1 sigma, it has only used one of those p. The second, the third is not used. So that's why it's not the most stable form of N2 as a gas, even though N cannot appear as one atom. It cannot appear as a monoatomic gas like hydrogen. It must be N2. But that N2, we have N triple bond N, which is made up of 1 sigma bond and 2 pi bond. Reaction of nitrogen. In contrast to carbon, nitrogen undergoes only 2 important chemistry or 2 important chemical reactions and did that at room temperature. The first one of this reaction is that nitrogen can react with lithium. You know, nitrogen is group 15, so it's more of non-metal. So it will be a non-metal to react with lithium, which is a highly electropositive metal. And when that happens, you will get lithium nitride. Lithium nitride can undergo a microbial degradation to get ammonia. And why do we say lithium nitride is Li3N? Why? Because Li is +1, is willing to give 1 electron. And nitrogen is willing to partake in a 3 bond system. And therefore, if you are using lithium as a positive charge, it will be +1. So nitrogen as negative charge will be -3. So when they exchange that for them, then it means 1 nitrogen will need 3 lithium atoms for them to be pleased in that reaction. So that +1 from the first lithium will give 1, second +1 will give 1, and third +1 will give 1. And nitrogen is 3. So they will now form Li3N. But one of the most important results we get in this lithium nitrogen reaction is that it's one of the main source of providing or preparing or manufacturing ammonia, because it will just take microbial degradation on lithium nitride to form ammonia. At high temperature, that's what happens at room temperature. But at high temperature, nitrogen's gas can react with more electropositive elements, e.g. the group 13 element, to give a binary nitride. When we are talking about binary, a binary compound is a compound that's made up of 2 elements, 2 atoms, or 2 different species, maybe in more than 1 form or 2 forms, but it's not more than 2 main group elements coming together. So what is this? Which it can form both covalent bond character and the ionic bond character. So binary compound of nitrogen with oxygen, with hydrogen, or other non-metal are usually covalent molecular substance. And of course, you know that immediately the non-metals are bonding with the nitrogen, they will be forming covalent bond because it is not by transfer of electron. Nitrogen cannot transfer electron because it's still looking for something. Oxygen cannot transfer electron because it's also looking for something. But the 2 of them can arrange themselves in such a way that their orbital can be provided close to each other and drop some certain amount of electron there for them to share and form a bond. That's why they are necessarily covalent bond. But if it is reacting nitrogen with highly electropositive metal, that one will give us, one of the example is group 13, which is aluminum. Aluminum is +3, nitrogen is -3. At high thermal condition, you can form aluminum nitride from that. Binary compounds of nitrogen. Few binary compounds of nitrogen are formed by direct reaction of the elements. And most of the time, they are done at very high temperature, because to fuse hydrogen gas or to fuse nitrogen gas or other things, it will need high thermal reaction condition to melt them, to atomize them, and then they can interact. So at high temperature, nitrogen gas reacts with hydrogen gas to form ammonia. However, if it is reacting with oxygen, it can form two different kinds or three different kinds of a binary compound: NO, NO2, and N2O. Why do we call them binary compound? Because each of these is made up of just nitrogen and oxygen, but the number of those atoms notwithstanding. So NO2 cannot be, you can't say it's not a binary because there are two oxygen and one nitrogen. We are not counting element by element. We are counting what is the difference. You have nitrogen and you have oxygen. It's a binary compound. So NO is a binary compound, N2O is a binary compound, and NO2 is a binary compound. And it can also form bond, triple bonded bond nature with carbon to form what is called cyanogen, as you can see that structure. The elemental nitrogen does not react with halogen. So it must be gas of nitrogen that you bubble at high temperature. The elemental form of nitrogen, which is nitrogen in one atomic, in one with just one atom, not N2, just N, does not react with halogen or other chalcogens. Chalcogens are the group 16, which are the oxygen family. Nitrogen halide, however, are noted to be formed using diatomic nitrogen at high temperature. So you can have nitrogen reacting to give NX3, where X is your halogen. You can have NCl3, you can have NBr3, you can have Ni3. But the first member of that group 7, which is fluorine, has a very high electronegativity than all other members of the group. So the trihalide of nitrogen of fluorine cannot be possible. So you can form trihalide compound with all group 7 elements except fluorine. Why? Because they are very toxic and is thermodynamically unstable and is highly explosive in nature because of short half-life. Reaction of the binary compounds of nitrogen continue. Unlike nitrogen oxide and nitrogen dioxide, unlike nitrogen dioxide actually reacts readily with excess of water to form mixture of two acids, nitric acid and nitrous acid. You remember every time you combine the non-metal with oxygen to form oxide of non-metal, they are always acidic oxides. NO2 is acidic oxide, SO2 is acidic oxide. Anytime you are forming between that group 5 and 7, you are combining them to form, they are always acidic. Or anytime you are taking the oxygen of the main metal of group 1, group 2, group 3, of group 1 and group 2, it will be basic oxide. And how do you confirm the acidity and the basicity of this gas? If you dissolve them in water, it will show by itself naturally. Nitrogen dioxide dissolving in water gives us nitric acid, HNO3, and nitrous acid, which is HNO2. That's why that is gas. Any acidic gas will dissolve in water to give us pure acid. If you dissolve SO2 in water, it will give you H2SO3, which is acid. If you dissolve CO2 as acidic gas in water, it will give you H2CO3, which is the one that constitutes the acid rain. Nitrogen also forms dinitrogen monoxide or nitrous oxide, a linear molecule that is isoelectronic with carbon dioxide. It's linear with bond angle of 180, just exactly like carbon dioxide. Nitrogen also reacts with semi-metal at very high temperature to produce covalent nitride. Semi-metal are just the metalloid. that there are boundary between the metal and the non-metal. So silicon is one, boron is another. And you know, the diagonal relationship makes the silicon and boron to be in some peculiar way that are similar. Ammonia, which is a hydride of nitrogen, is one of the few thermodynamically stable compound of nitrogen, which upon oxidation with excess of oxygen can give us pure nitrogen gas and water in form of gaseous states. Uses of binary compounds of nitrogen. The binary compound of nitrogen. About 10% of annual ammonia production is used to make fibers and plastic with amide bonds. Fibers and plastic that have amide bond in repeated units, we call them polyamide bond. Example of such polymer is nylon and polyurethane. And you know how nylon is very important in our day-to-day business, in packaging, in material, and polyurethane is useful in formation of foam that we are sleeping on, and so many other things. 5% is used in explosives, such as ammonium nitrate and TNT, the highly reactive compound that they use in nuclear weapons and atomic bomb-like nature. Trinitrogen toluene and nitroglycerin. Large amount of anhydrous liquid ammonia are actually used in fertilizer. You remember that there are different types of fertilizer. We have NPK fertilizer, we have other things like that. Hydrazoic acid is acid that is formed with molecular formula of HN3. It's just like an azide reacting with an hydrogen. You know, hydrogen, remember what we have said, your hydrogen, if it is acting, it can act as a positive, it can act as negative, so its position is unique. So if hydrogen is +1, nitrogen in azide has 3 nitrogen that have -1. So when the two of them relate to drop 1 for each other, then hydrazoic acid is HN3. So don't confuse this thing with ammonia. In ammonia, nitrogen is a positive charge. In ammonia, nitrogen is there and hydrogen is there. But when you look at that, that nitrogen is only 1 atom of nitrogen. Unlike this one, 3 atoms of nitrogen with -1. So whatever this one is, you remember that the reaction will involve dropping 3 electrons from here, 1 from here, and you have that attraction to form NH3. So HN3 is different from NH3. In NH3, which is ammonia, you have only 1 nitrogen and 3 hydrogen. In HN3, which is hydrazoic acid, you have only 1 hydrogen and 3 nitrogen. Then hydrazine is another thing. Hydrazine has 2 amine bonds together. It's very useful in organic reaction because of the 2 lone pair of electrons that are on those 2 nitrogen. And this is what we use even in testing for carbonate of aldehyde and ketone. This is hydrazine because it can condense with carbonate of aldehyde and ketone to give color precipitate. And then because of the highly explosive nature this one is, it is used as rocket propellant and to inhibit corrosion in boilers. But if you want to use it for the students, you turn it to a derivative of itself, which loses one of the hydrogen for phenyl group to come in. And when that phenyl group come in, you now have phenylhydrazine. And this phenylhydrazine, we have a nitro group on position 2 and another nitro group on position 4. This is what forms what is called 2,4-dinitrophenylhydrazine. That we call DMP, which you use to test for presence of carbonyl of aldehyde and ketone. And when that happens, this combines with the ketonic carbonyl to form color precipitate, which you can now be able to confirm that, oh, because this one gives a color precipitate in the 2,4-DMP, therefore carbonyl of aldehyde and ketones are present. These are the class activity that we can look at for the group 15 element. Why is it difficult for nitrogen to form long chain molecule, unlike carbon that can form long chain molecule, despite the fact that both of them have sp3 hybridization? And when we look at that, we mean that because in sp3 hybridization for nitrogen, there's a lone pair of electron on him that he has not used, making it to be electron rich and negatively charged inside, because electrons are negative charge. So immediately another nitrogen is coming in to join with him. The lone pair of the first one and the second one will be pushing themselves away. If it has been positive and negative, it will attract each other. But both of them are electron which is negative, so the highest it may form is not going to be more than 3 nitrogen. After that, no more. But carbon can form 10 carbon as you have it in decane. It can form 50 carbon. It can form 1,000 carbon as you have it in carbohydrate and biomolecules. How can you prepare nitrogen in the laboratory? We have talked about that. It's part of what we have just discussed. So we already know that. What is the product of reaction of nitrogen with semi-metal? If nitrogen is reacting with the semi-metal, what will be the product? Highly and less electropositive metal at high temperature. Compare the product with those of carbide and boride. So we are saying that carbide is in group 4, boride is in group 14, boride is in group 13. So we compare that, we discover we have said moving with semi-metal, we have said some things here. So all you need to do is to go back to what we have just discussed and then relate with it. If you cannot get it, you can ask it next class so that we can look at it. What is the interaction that is simple between the transition metal and the nitrogen, the boron, and the carbon? You remember what we call interstitial compound. When this group of 13, group 14, group 15 are reacting with transition metal, they form the interstitial compound. I don't need to go back to that because we have already discussed it at length in the carbon family. So that takes us to the second group that we are going to consider today, group 16. Group 16, of course, you should know what are the elements that are there. We have the oxygen as the first, followed by sulfur, followed by selenium, followed by tellurium, followed by polonium. Polonium is sometimes separated from them because as you go down the group, radioactivity property becomes the order of the day. So polonium is a radioactive element which is used in nuclear energy to power plants, and it's also used in nuclear war. Polonium actually was discovered by somebody that was from the soil of a country called Poland, and to use it to actually give the recognitions and the honor to the country, he gave that name polonium. If you are looking at group 16, it should not be difficult for any one of us to write electronic configuration of every one of them. All you need to know is what is the noble gas that is before it. We are looking at oxygen. What's the noble gas before the oxygen? Oxygen has atomic number of 8. And the first noble gas is helium. The second noble gas is neon, which is 10. So oxygen itself is not up to 10. So you will need to fall back on the helium. The helium, which is 1s2, then 2s2. You know, in the valence shell, you have 6 electrons. 2 is in the s orbital. 4 will be in the p orbital. So this is shorthand form for the electronic configuration of oxygen. If you want to do electronic configuration of sulfur, sulfur has atomic number of 16. And that means what is this noble gas that you will find before 16? 10. Because 10 is neon, 18 is argon. So you can't go to 18 because sulfur itself is not up to 18 electrons. or proton number. So you can say neon will have taken care of the first 10 electrons. So 6 electrons is what you want to fill in your sulfur. But now neon is in period 3. So it will be 3s2, 3p4. If you want to know the electronic configuration of selenium, it's the same thing. You get the noble gas and you continue the thing. But we have said that instead of this noble gas, if you want to let it long, it depends on you. You can start it all the way from the scratch. And that will be 1s2, 2s2, 2p6. This what you have written here is the whole lot for neon. Then you can now say, okay, 3s2 for the 12th electrons and 3p4 for up to the 16th electron. This is for sulfur. This is for sulfur. But what we have just done is that instead of this, that's 10 electron, which is for the neon as a noble gas, you can replace it with neon. So the first thing is that you must know the elements and you must know how to do their electronic configuration. Then a lot of things becomes easier. The family of group 16 elements, initially they were called the oxygen family. You remember, every of the first elements in each group is what they used to call the family of that compound. But that oxygen family is also commonly called chalcogenes. Remember, nitrogen is nicogenes. This group 16 is chalcogenes. These elements are found in nature in both free and combined states. Oxygen is needed at times throughout our lives. Sulfur is also one of the essential elements responsible for some of the protein structure in all living organisms. In fact, when you are talking about the essential amino acid that is responsible for the coiling of the human hair, that will make some hair to just go long strand and some hair will just be coiling, is the number of the quantity of the amino acid called cysteine that is in the human hair, that is showing why some persons' hair are coily and round, but why some other ones are long and strand. So when you are doing retouching and all those things on the hair, you are trying to break that sulfur bond in the cysteine to elongate the hair. And that's why a majority of life on Earth will be difficult or may not even exist without this chalcogenes family. Oxygen, without man bringing in oxygen, man cannot be alive. And a lot of amino acids, sulfur is important. You remember cross-linkage of sulfur is what caused the vulcanization of rubber that makes us to have a tougher strength things that are called tire we use for our car. And why it's different from the soft nylon-like polymer. After what makes it happen is cross-linkages with sulfur. And that's what is called vulcanization. So vulcanization of that soft semi-solid rubber is what toughens up to strengthen the bond to make tire that it can even stand to carry the rim and to carry the car to thousands of kilometers without busting. Sulfur is what gives that. Many industries utilizes sulfur. In fact, sulfur is also good in treatments of a lot of infection, the skin infection, the hair infection. You have sulfur, you grind it, you mix it with some cream. It can do a lot of healing magic for anybody that have problem of dandruff and so many other things. So it is medicinal also. But the emission of sulfur compound is often seen more as a problem than the natural phenomenon. Because when sulfur is emitted, you can be rest assured that oxygens are in the atmosphere that can combine to form sulfur oxide, sulfur dioxide, which are acidic gas. When SO2 has water in contact through the rain and through any other thing, you will form H2SO3, which is a little weaker acid. And when you oxidize that SO2 to SO3 before the water is added, you get H2SO4, one of the strongest and highly concentrated acid in nature. It's industrial feedstock, but outside of using it for the industrial purposes, it must be carefully handled because it can also do damage to human life. So many industries uses that, but the emission of sulfur compound is often seen more as problem than the natural phenomenon. The element polonium has no stable isotope because they have a very, very long half-life. And the isotope with mass of 209 has the longest half-life of 103. So polonium is a radioactive element that is used in nuclear weapon and then nuclear energy generating cell. Property and periodic trend. Property of oxygen are very different from other elements of the group. You remember we have said that the first member of every group in the main group element, they are at the second period, and their chemistry, their property, their behavior is always far different from other members of the group. So oxygen is not an exception. If you look at oxygen very well, you can do some things that you find it difficult to even see what has happened. Because when we are talking about the higher the molecular mass, the higher the tendency of compound to be solid in nature. And the lower the molecular mass, the higher the tendency of something to be gaseous in nature. When you look at the hydride, if you look at the hydride of sulfur and the hydride of oxygen, you will see that peculiar nature. If oxygen is having atomic number of 8, and you are combining it with hydrogen, you will form H2O. So molecular weight of this will be 16 plus 2, 18 grams per mole. However, if you are looking at hydrogen combining with sulfur, you have what is called H2S. With sulfur is 32, hydrogen is 1 times 1, 2. That will be 34 grams per mole. You see this one has defeated the law. You see here now, H2S have a heavier mass. We're expecting that H2S should have been like the solid and H2O should have been like liquid or something. But when we see the H2O should have been the gas, sorry, because of the lower weight. And this one should have been the liquid or the solid. But when you see it, at room temperature, water is liquid. At room temperature, H2S is gas. The peculiar behavior of water, why it's able to exist in liquid form at room temperature, even far, far higher than H2S, which is now gas, is because of those unique properties of oxygen. And with hydrogen, it has power to form hydrogen bonding, which makes it to now have a high melting point and boiling point. The boiling point of water as liquid is 100 degrees centigrade. Whereas H2S is a gas, mere opening it without much heat, it's already evaporating. Another thing that have that existing nature of that oxygen in the chalcogen family is that this is the only one of this group 16 that can exist in all the state of matter. Water can exist in gas form if you heat it up. Water can exist in liquid, that's its normal room temperature form. And if you freeze it, water can exist as gas. That's why you can talk about ice, you can talk about water, and you can talk about steam. So these are part of the peculiar nature of oxygen that is very important for us to look. And if you remember what we talked about, the electronic configuration, what you are having here is already what I've described earlier, if you still remember. And what you have described earlier is that sulfur, we have 1s2, 2s2, sorry, this thing is having an omission here. Oxygen is 1s2, 2s2, 2p4. And that makes 8 electrons, which means in the first orbital, or the number 1, there are 2 electrons. And in the second orbital, there are 2 electrons in the S and 4 electrons in the P, making total of 6 electrons in the outer shell. But when you look at sulfur, it will be 1s2, 2s2, 2p6, 3s2, 3p4. So here right now, is the electronic configuration of something that have atomic number of 10. And that's a noble gas. And that is neon. So if you put neon here, you could just say 3s2, 3p4. And that is how it goes down, 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 down. So please correct that. Correct that in your course material. I lifted it from the course material. So this one will be 2s2. The next to it will be 2p6. So there's a omission of 2 here, which you need to put. And next to that is 3s2, which is correct. Next to that will be 3p4. 3p4. So there's a 3 in front of that p4 you need to insert. Likewise, the same thing for this 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p4. And the same thing here and here. So if you look online, you can see the electronic configuration of them, or the periodic table that we shared earlier on. The property of oxygen are very different from the element I've explained, but they all have minus the 2 electrons in the outermost shell. Minus 2 electron means that they borrow 2 to become a non-metal. And when that happens, oxygen will be having O raised to power -2. So oxygen exists in -2 states. And you know anything that exists in minus is actually coming from the non-metal. So we need a metal to bond with it. Let's say, for example, we want to talk about the group 1 oxide. Oxide of group 1, let's say, for example, I have sodium. In the normal setting, sodium is +1. It wants to give 1. The oxygen wants to take 2. So it will take 2 of the sodium to donate to oxygen before they can form bond. So at the end of the day, what you have is Na2O. So when you say sodium oxide, this is it. And because it's the oxide of the group 1 element, which is the metallic part, it is a basic oxide. And you can see that clearly by the time you dissolve that oxide in water, it will form sodium hydroxide, which is a strong base. So let's look at some of the things. So you know that the oxygen have oxidation state of -2. Sulfur can exist in other oxidation states because it is below the oxygen. So it has a tendency to expand this octet, because when you come to sulfur, you're already coming to 3s orbital. And at the 3s orbital, you have a low line d orbital that can be energetically favored if you have some electron to put. That's why sulfur can form expanded octet. Sulfur can form SF6, SF5, but oxygen cannot do that. Oxygen cannot exceed octet. So while selenium, tellurium, and polonium has other oxidation states of +2, +4, and +6. Periodic trend of the chalcogenes. These are the periodic trend of the chalcogenes. We have discussed all these things right from the beginning. We are just trying to look at it, how it's now applicable to this group 16. Remember, we have discussed atomic radius, the ionic energy, ionization energy, ionic radius, electron affinity, electronegativity. So metallic property of this increase in the order. You remember that as you are going from left to right across the period, metallic property will be reducing. So we can say group 1, sodium, is more metallic than group 2, which is magnesium. Magnesium will be more metallic than group 13, which is aluminum, that is in that line, and on like that. As this metallic property is reducing, you know that non-metallic property will be increasing. So oxygen will have the lowest metallic property. So metallic property reduces across the period, but it increases down the group. So polonium is like almost like a metal, despite that is in group 16, that should have been -2, because as you are going down, the metallic property is increasing. So oxygen have the lowest metallic property. So its metallic property is lower than that, or is less than that of sulfur. That of sulfur is less than that of selenium. That of selenium is less than that of tellurium, and that of tellurium is less than that of polonium. Polonium is a metal discovered. You see, it's purely a metal now because of that place. And that's why the fact that group 16 should have been non-metal. Polonium is a metal discovered by Maria Curie, who named it after our country, Poland. And you can see some of how these boiling points, ionization energy, and ionic radius varies across down the group of this compound. General property of oxygen. Oxygen is colorless, odorless, and tasteless gas at room temperature and at 1 atmospheric pressure. It's most abundant element by the mass. You remember we are talking the other time that nitrogen is the most abundant element. But here by the mass, when we are talking about the weight, oxygen is more abundant than nitrogen. Remember that nitrogen has atomic number of 7, oxygen have atomic number of 8, and the metric tons of that, it will reflect that 1 unit difference. We always reflect. So it's the most abundant element by mass. Remember that word, by mass in Earth's crust and in human system. In fact, most of your group 1, group 2 and group 3 metal, they are found inside of the soil in combination with oxygen. When you are talking about alumina, Al2O3 is found inside the ore of the earth as an ore, which after you have done the extraction, you are able to get aluminum out. When you are talking about magnetite, hematite, and all those bauxites, you know, all those ones are oxide of this main group element that is found in the earth crust. Oxygen is very valuable for man because oxygenated and deoxygenated blood going out and returning is what actually refresh life and make the red blood cell to keep living. It is used in the manufacture of iron, steel, and other chemicals. It is also used in water treatment. But this one we are talking here right now, we are talking about an allotrope of oxygen. We are talking about the allotrope of oxygen. You know, there are 2 different allotropes of oxygen. Oxygen can appear in a divalent nature. That's what we call O2. That's oxygen gas. And it can appear in a trivalent nature, triatomic nature. That is O3. That's what is called ozone. Oxygen is used in those things, but ozone is used in water treatments, is used in the manufacturing process, is used actually as an oxidant in rocket fuel and for medicinal purpose and in the petroleum refinery. Compound of oxygen are more thermodynamically stable than the O3. The compound of oxygen are more thermodynamically stable than the oxygen dimolecule itself. So what we are trying to say is that if oxygen comes together with itself to form oxygen gas, it cannot be stable under high heat condition. But if oxygen combined with metal like sodium to form sodium oxide, wow, it will withstand high thermal reaction to stay as a stable product. General property of the ozone, which is the allotrope of oxygen that have 3 oxygen. It is a pale blue poisonous gas with a strong odor and a stronger oxidizing agent than oxygen gas. Ozone can substitute for chlorine in purifying drinking water. In the absence of chlorine, for the water purification, you can use ozone. But there's something you must note when you are using ozone. Ozone, you remember we said it's not that stable because of the 3 atoms of oxygen, which want to rearrange or give one away to have other things done. It's not as stable as chlorine gas. So it can disappear and leave water unprotected from bacteria. So its long-lasting effect is not as long-lasting as that of chlorine when you are talking about the treatment of water. Because of its instability, it can rearrange itself from being ozone and therefore lose its power to protect the water from microbial growth. And that will lead to infection if you are not careful. So if anybody is using ozone, there's from time to time, they must monitor that the ozone is not disintegrating and they are replacing it from time to time to make sure that the strength is there. Ozone at a very high altitude in the atmosphere is responsible for protection of the Earth's surface. You remember that in environmental sciences, we know that there's a thick blanket that nature has put on top of us to screen away the ultraviolet rays from the sun, so that it will not come directly to the heart, because coming to the heart can cause cancer, skin cancer, and so many of that terrible things. But the industrial activity of men has pushed too much smoke onto the sky, which has now perforated this blanket called ozone. And some of the traces of ultraviolet ray from the sun are already hitting the heart. And this is leading to so many things. And that's why when you go to the Arctic region of the earth, where you have the highest land, the high rate of radiation from sun is now melting those ice, and there is rise in the ocean current, and water is flooding into the system because the volume and the capacity of liquid water has been increased because of a lot of ice that has been melting in the Arctic region and Antarctic region of the world. So ozone at high altitude is a good protection against ultraviolet rays that is not good for man. However, if it appears at low altitude, close to the human line on Earth, it becomes a major component of smoke, and that is not good. The reaction of oxygen and its compound. Oxygen's primary oxidation is actually -2, -1, and 0. And some of the time it can have -half oxidation state anywhere you have O2 having oxidation state of -1. This is one of the uniqueness of oxygen, being able to form 3 different kinds of oxide at the same time. But this -2 is the most common oxidation state for the oxygen. When oxygen reacts with metal, it forms basic oxide that are mostly ionic in nature because they can dissolve in water and react to form base. That's why we call them basic oxide. For example, the one we are saying, sodium reacting with oxygen will give us sodium oxide. And I hope we know how we have this, because it is for you to balance the equation. Or if you want us to balance the equation, we can look at it. Sodium has normally +1. Oxygen normally has -2. When the two of them combine, there's a donation because plus and negative, 2 comes here and the 1 comes here. So when you say sodium oxide under the oxidation state of -2, this is what you will have. But this is not balanced. So there are 2 sodium here right now. So we need to put 2 here to balance the sodium. But here there are 2 oxygen here, and there is 1 oxygen here and 1 oxygen here. So there's 1 oxygen here, sorry. This is the product of reaction. That's why I put it in the square bracket. So we see that the oxygen is not also balanced. So if we have to balance oxygen, we must increase it here until you are fully balanced in everything. So when you put 2 here, the oxygen is balanced, but sodium is not balanced. Then you put 4 here. 4 atoms of sodium with 1 molecule of oxygen will give us the 2 molecules of sodium oxide. This is a basic oxide because it can easily dissolve in water. Being an ionic compound, it dissolves in water. What did it form? It forms sodium hydroxide. So oxides of non-metal are covalent in nature. They share their electron, they don't transfer. Therefore, they lead to forming the acidic oxide, CO2, SO2, SO3, NO2, NO, PO2, all those things are. So you dissolve in water and you can do that to others. Monoxide, oxide of the main group elements can appear in various forms. So the first one is monoxide. Monoxide occurs when the oxygen is at oxidation state of -2. It combines with sodium to form Na2O, sodium oxide. It combines with calcium to form CaO. Why? Because calcium has atomic number of 20, 2882. So he has +2 that he wants to give out. And oxygen has -2 he wants to receive. So the 2 cancel 2. So when you are talking about calcium oxide, it will just be CaO. But if you are talking about aluminum oxide, aluminum has atomic number of 13, 283. So it has 3 electrons that he wants to give out. And oxygen is in normal -2 state, have -2 to receive it. So in order for it to balance, the two come to the base of aluminum, the three come to the base of oxygen. So anytime you are saying oxide of aluminum, normally it should be Al2O3. So other oxidation states of oxide that are available is when it has -1. And what we have there is peroxide. We have peroxide. Hydrogen peroxide, sodium peroxide, barium peroxide. However, if it is at -half oxidation state, that means diatomic oxygen with -1. It forms what is called superoxide. Superoxide. Superoxide, not peroxide again. Oxygen reacts with hydrogen to form water. We all know that reaction. It's easier to comprehend. And oxygen is a large number of organic and inorganic molecules. Sulfur is another member of that group. Sulfur forms a wide range of allotropes, unlike oxygen that is just only ozone and the oxygen gas. Sulfur can form 5 different kinds of allotropes, but the most stable of it is S8 and is solid in nature. Other ones are S, S2, S4, and S6. These are possible because of the ability of the sulfur to expand the object. 2 common oxides of sulfur are sulfur dioxide and sulfur trioxide. They are both acidic oxides because they can dissolve in water to form acid. They are used in the production of sulfuric acid, which is used in a variety of reactions. H2S, of course, that's hydride of sulfur, is poisonous gas, incapable of forming hydrogen bond. That's why it's gas. Where H2O is capable of forming hydrogen bond, is liquid, despite the fact that it's lower in molecular mass than H2S. H2S can be recognized by its strong odor. It smells like a rotten egg. So anytime you have sulfur attached to anything, the suffix in front of that name will change to accommodate the sulfur that has come in. And that is by including thio. So if you have something like phenol, and the oxygen in that phenol, which is OH linked to benzene ring, is changed to SH, then it's called thiophenol, because the oxygen has been replaced by a lower member of this group, which is sulfur. There are so many other compounds of sulfur that can be formed, organic and inorganic in nature. We have the thiol, we have thiophenol, we have organic sulfide, we have disulfide, so many of them, alcohol and thiol. Thiol means when an alcohol OH becomes SH. Mercaptan is a compound of alcohol that have SH index of OH. You can call it thiol or you can call it mercaptan. Selenium, the summary of selenium is as what we have presented here. Selenium is red and black amorphous solid, or it could be red or gray crystalline structure. The gray crystalline structure is the most stable of selenium. Selenium is more metallic than sulfur. You remember metallic power increases down the group. It acts as semiconductor and in production of rectifier. All these panels of the computer, the microchips of the phones, all these are used as semiconductor to make them. They are also used in the rectifier, which is diode, for converting the alternating current, direct current to the alternating current, which you find in the transistor. Selenium is photoconductive, which means that in the presence of light, electrical conductivity of selenium will increase. It is used in drum and laser printer and photocopier machine and plumbing brasses. It is found in soil and plant tissue that have bioaccumulated elements. Many animals require it as a micronutrient, but toxic when it becomes large dose. A micronutrient is something that if it appeared in trace quantity, it can benefit human system. That's why we call them the micronutrient or trace element. But when they appear in a large dose, they become problem for man. So it's in glutathione peroxidase, which is very good in anti-aging property, has good anti-aging property because it has the tendency to destroy the lipid damaging peroxide. The correlation between selenium deficiency and an increase in HIV risk has been recently proposed by scientists. That deficiency of selenium can actually increase human chances of easily contacting the HIV. Tellurium is the next one. It's a metalloid which can behave like metal and non-metal. It's like a semi-metal of oxide family. It is silvery white in color, and its metallic cluster similar to that of tin at room temperature. Like selenium, tellurium also display photoconductivity. Photoconducting nature of this is what makes them to allow them to make their electron to jump from one energy state to another, whereby the energy is quantized, and then there's bandwidth that is covered in absorption and emission radiation. It is used in metallurgy in the combination of copper, lead, and iron. It is used in solar panel and memory chips for the computer. It is not toxic or carcinogenic. That means it's not toxic and it's not causing cancer. However, when humans are exposed to too much of it, they develop a garlic-like smell on their breath. Polonium is the last and not the least. Polonium is rare. It's radioactive elements in group 16, and it has 33 different isotopes. It exists in a variety of states and has two metallic allotropes. It dissolves easily into dilute acid. Remember, because it's having higher metallic property. Polonium does not exist in nature in compound, but it can form synthetic compound in the laboratory. It is used as an alloy with beryllium for nuclear weapons. Polonium is highly toxic. It emits dangerous radiation. It can cause cancer if chronic exposure to radiation occurs. Best option for treating humans who have come in contact with polonium involve the use of chelating agent, like your aluminum oil gallate, like glyoxan. They have low of electron they can use to donate to form a metal complex with the polonium in order to address it away from the human system where it is causing trouble. So these are other activities which you can try before our next class. And if you have any issue in any of this one, then you can let us know. This is the first 5 members of group 16. That should not be difficult anymore. The first member will be the oxygen, sulfur. After sulfur, we have selenium, we have tellurium, and it goes on like that till you get to polonium. With the information of oxidation state only, differentiates between oxide, peroxide, and superoxide. So you can use sodium. So when oxide is formed, oxygen is -2. So when it combines with sodium, it becomes Na2O. If it's peroxide, it's at -1 oxidation state, it's Na2O2. And if it is superoxide, it's O2 with -1, which can combine to form NaO2 at -1 state, +1 state to form a compound. What sulfur type is the most stable or is the most common state and why? Sulfur 6, solid at room temperature, and the silent thermally stable. At the end of today, in summary, we have been able to, 1, know and classify the elements in group 15 and 16. We said the elements in group 15 are nitrogen family, or you can call it nitrogen family, or you can call it the group 15. And we said the first element in that group is nitrogen, followed by phosphorus, and going down that way. However, we said in group 16, it is called the oxygen family or chalcogens family. The first member is oxygen, followed by sulfur, followed by selenium and tellurium, like that. We have also been able to understand the electronic configuration of this group 15 and 16. You can draw them in shorthand form, considering the noble gas before them, or you can draw them in the expanded form, starting from the beginning, which is 1s2. You have been able to know various reactions that are peculiar to group 15 and group 16 elements. And we have also known the application of some of these elements in group 15 and group 16. It's on this note we have come to the end of this class. I want to thank and appreciate you. And by God's grace, we are meeting on Friday for our last facilitation, which is the week 8, topic 8. And there we'll be looking at other higher main group elements, which is group 17 and 18. Thank you very much, and God bless.